Okay, so it's 10 o'clock. We're going to get started. The question that we have today is a question about programming. Is very similar to the one we left off with last time. That one, you had to make a matrix where the ij entry was I minus j. And this is very similar. You want to make an ij matrix whose entry is xi minus xj, where x is some array that was given to you. So this is what I call the pairwise difference array, or the pairwise difference matrix. It has the pairwise difference of xi and xj. Of course, it'll have zeros all along the diagonal. And here is one solution with for loops. So last time, most people said they were pretty comfortable with this kind of Python stuff. So maybe a lot of people have this for loop solution. And now we're going to talk about a different solution. So today's going to have some programming stuff baked in. I'll give you one more minute if you haven't answered it yet. I only have 6 answers so far, and there's a few more than 6 people. So one more minute, and you just have to guess, how long do you think is the alternate solution? So the for loop solution took 50 seconds. How fast is the alternate solution? And yeah, you have to guess how fast you think it is. All right. Okay, so we have 15 people in the room, so hopefully we'll get up to around 15. This is also a good time if there's any questions or comments about anything.
It is matrix subtraction, I guess, right?
I want a matrix whose mij is xi minus xj. That's right. Okay, let's stop. Before I do the answer, so if you haven't put your answer in, you'll have another couple seconds while I make a super quick announcement that I just thought of, which is that next Tuesday, so 1 week from today, there is a data science colloquium. So colloquium is from, I don't know how to spell it. Colloquium is from the Latin for talking, and that means we're going to have a speaker who's coming from the University of Toronto who does some interesting things about data science and has a new book on LLMs and that kind of thing. So I hope you guys will all go. It's at 11:30, so it's immediately after this class. So we can all head over there together. It is somewhere near the math building, near McNaughton. I think it's in SSC, which is right connected to McNaughton. So I'll make sure to email the announcements, but put it in your calendar. 11:30 Tuesday, so 1 week from today. 1 week. So I really hope you guys will go. Okay. Let's take a look at the answers here. So 12 answers. What did people say? Reveal the counts. All right. So looks like most people picked less than 1 second, and the correct answer is less than 1 second. So the for loop method is way, way, way bad. It takes 50 seconds. The actual solution, not only does it take less than 1 second, it takes 1/5 of a second. So it's 250 times faster than the for loop way. And so if you do this for loop way in Python, of course it will work, like you get the correct thing, but you will really your hands will be tied with what you can possibly do in Python unless you learn these array broadcasting ways and sort of thinking of everything in terms of vectors. So it's really important you try to do that if you want to be, at least if you want to do data science in Python or machine learning in Python, you cannot write code like this that does for loops. It will just be too slow. And the reason is that Python, when you do write a for loop like this, it does it in Python. And Python is an interpreted language. And your computer is really going to go through and go like, okay, now I equals 1, now I equals 2. And it really takes its time. And it's all very slow. But if you do it sort of using vectors and these array broadcasting things, Python doesn't actually do it. It sends the computation to a C program. And that C program is very fast. So Python is sort of the wrapper around the NumPy programs, which are written in C. And if you do it that way, you can get pretty good performance. And you know, it's not as fast as other things, but it's still fast enough to be useful. If you write code like this, though, it will be very slow. So let's talk about how to do it. And I made a little sheet over here. So this is where I have this thing. So here is how I did this. Let me see. What does this look like for you guys? Okay. I wish there was a way. Is there a way I can hide this? Oh, look at that. Okay, great. That's a little better. Okay, so this is in a Google Colab. Can I make it light mode? Dark. Let's try light and see what that looks like. Okay, is that a little better? That's a little better. Okay. So import NumPy, n was 10,000, and we can do this for any x, but I just put x to be some random numbers to make a vector of size 10,000 comma. Okay? And it's important you know about these 10,000 commas. A lot of people think of column vectors or row vectors, which would be 10,000 comma 1 or 1 comma 10,000, but NumPy has this extra thing, 10,000 comma, which is neither a row vector or a column vector. You got to be careful with these. There's a lot of bugs that can happen if you think it's a comma 1 and it's actually just a comma. So this only has one dimension of size 10,000, and that's what we're working on. And here is the for loop solution for I equals 1 to n, for j equals 1 to n. Mij is xi minus xj, and this takes 50 seconds. If you put in this command %% time it, it will run it and tell you how long it took. R1 means run it once. So dash R1 means run it one time and tell me how long it works. If you don't put an R1, I think it defaults to running it 3 times and taking the average or something. So if you just want a rough estimate, R1 is great. So I'm going to show you a couple different solutions. And here is one. Yeah, any questions or comments? Okay. So feel free to stop me here. If there's any programming questions, this is a good class to ask. We're going to do some programming stuff. So here is one way to do it using np.from function. np.from function. And np.from function will apply a function to all of the indices ij. There's also a command called indices that gives you a matrix of all the indices. And np.from function is basically doing indices and calling the function on it. So here is another totally valid solution. You make this thing myfunc, which returns xi minus xj, and you call from function on it, and it'll apply what you want. So this is a pretty good way to do it. This is okay. It takes 1.36 seconds, so it's not bad. The reason this one isn't quite as fast is because you're actually still calling xi and xj. So this is a lot better, much, much better. There's no for loops anymore. But when you call this, you have to actually go and from the array x pull out indices like xi. What is x1? What is x2? What is x3? And the best kind of way you can write your NumPy code in code that uses arrays is to try to do everything with vectors so you never actually see xi and xj. So can we write it only with just x, the whole vector? And that will be much faster. And the reason that's much faster is because when the computer stores the vector x, it puts it all in memory next to itself. So if you can write code that says, just take the vector x and do the things to it, instead of doing it entry by entry, it can do big chunks of the vector in memory. That's why it goes a lot faster and it's optimized to do that. So anytime you can write code like this, okay, that's like good. If you can write it without actually saying x square bracket I, it's even better. And that is the solution I was talking about, which is less than 1 second. And here it is. It's one line. This is what it looks like. And it only takes 214 milliseconds. So 6 times faster than this one, and 250 times faster than this one. Okay? And waiting 0.2 of a second is totally legit. Well, waiting 50 seconds to do one simple step is going to take you all day. You will not get more complicated things done. So I'm going to explain how this one works, because this uses array broadcasting, which is a really important trick when you do this stuff. So if you know array broadcasting, you're probably like, okay, of course it works. But if you don't, this looks like total mysterious magic. What the hell is np.newx? It's all of a sudden, it actually calculates it. All right. Any questions or comments before I explain this array broadcasting stuff? Who's seen a lot of array broadcasting before? Who's never seen array broadcasting or never done it else? Okay, great. So I'm going to go over it slowly. I think it's a really good trick to know. And it really is the key to writing all of your code so that you don't have to do for loops and don't have to do things like this, is to learn array broadcasting, and that is a really important way you're going to manipulate vectors and things. Of course, sometimes you can't avoid doing a for loop, right? If the next step really depends on the previous step, you cannot avoid a for loop. But a lot of times you can do tricks like this, and it really will make your code a lot faster and more efficient, so you can do more things and do bigger data sets. So let's talk about what this does. So array broadcasting. Array broadcasting. And there's also a video about it with an example as well. So in array broadcasting, you are taking vectors and telling the computer, I want you to think of this vector as a matrix with all of the columns repeated. So it is a method by which you can take a vector. So here's an example. You can take a vector. Let's take the vector 1, 2, 3. And we're telling the computer by array broadcasting, we tell it, please copy this some number of times. So you can go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's a way to copy a vector many times. And once you have a copy like that, then you can do things with it. So in our example, let's pretend we took 1, 2, 3, 1, 2, 3, 1, 2, 3. Let's do it 3 times. Like that. And let's take this one. Let's take 1, 2, 3 this way. And let's copy it vertically 3 times. 1, 2, 3, 1, 2, 3, 1, 2, 3. And now if you take those two matrices, where 1, 2, 3 has been copied 3 times, and you subtract them, then you subtract. Then you're going to get exactly the kind of thing we want. 1 minus 1 is 0. 1 minus 2 is negative 1. 1 minus 3 is negative 2. 2 minus 1 is 1. 2 minus 2 in the middle here is 0. 2 minus 3 is negative 1. Okay, and so on. 2, 1, 0. And that is exactly the kind of difference matrix we want. So by copying the vector into a matrix, we can all of a sudden do things where the output is going to be a matrix. So this array broadcasting is the step of copying like this. And how do you do it in NumPy? The rule is, whenever you do an operation like subtract, so it's automatically baked into when you subtract something. So when you subtract, NumPy will automatically copy. Here's the rule. Here's the rule. NumPy automatically copies whenever the size of a dimension is 1. Is 1, and the other size is not 1. What do I mean by the size of one dimension is 1 and the size of the other one is not 1? So here, if I take the vector 1, 2, 3, and it's a column vector, the dimensions of this are 3 rows, 1 column. It really is a 3 by 1 column vector. And if I take 1, 2, 3, that really is, as a dimension, a 1 by 3. 1 row, 3 columns. And so if you take this vector, 1, 2, 3, of dimension 3, 1, and you take the vector 1, 2, 3 of dimensions 1, 2, 3, and you tell NumPy, please subtract these. When you go and you write the subtraction, it will automatically do everything I just said. And so the output will be this matrix, 0, negative 1, negative 2, 1, 0, negative 1, 2, 1, 0. And the reason is, what it is doing, it compares these things. It says 3 and a 1, so I will take, because there's a 3 and a 1 here, I will copy this one 3 times. And that is exactly making this matrix. And when it sees the, let's do this in, say, this green. When it sees a 3 and a 1 over here, it says, oh yeah, there's a 1 here and a 3 there, so we're going to copy that 3 times. It's going to make this matrix. And then it will subtract them. So if you say, please subtract this vector from this vector, it will automatically do that. Let me show you in the code so you can also see how that works. Let me make a new code block here. New code block. And so I'm going to make, let's call this column is going to be np.array. And I want it to be 3 numbers, 1, 2, 3. So 3 rows, 1 column. So the way I'm going to do that is like this, 1, comma 2, comma 3. And hopefully this will work. There's always a danger when you live code. Yes, okay. Does anyone know why it's not going to run? It's not going to run because I didn't run. You have to run this line first to import NumPy, otherwise nothing works. Okay, good. So there we go, there's column. And a nice thing about using Google Colab rather than doing your own thing is you have this variable explorer over here. And we can see that column, if you mouse over it, column is a 3, 1 thing. So 3 rows, 1 column. And here it is 1, 2, 3 as a column vector, exactly as we want it. If you were doing this in just regular Jupyter Notebook, you would have to type in something like print column.shape or something like that, and it would say 3 by 1. Okay, so that's good. Let's also make row, which is np.array of 1, 2, 3. Why are you, did I type something crazy? Okay. And I will run that. And now I can see over here, hopefully row has been added. Yeah, row is shape 1, 3, and there it is, 1 row, 1, 2, 3. Okay. And I suppose I can maybe zoom out a bit here. Okay. So I made a row and column, and now if what I'm saying is correct, what I just told you, I'm going to call that the answer is going to be column minus row, and there we go. It made answer, and let's ask it. Please print answer.shape. And if everything I've said is not a lie, it should say 3 by 3. Let's see if it works. 3 by 3. Okay, there you go. So what it does is it takes column and it stretches column out, makes copies of it to make the thing I said. It takes row, it stretches it the other way, it copies itself 3 times, and at the end you get a 3 by 3. And what is answer? It should be that matrix that I said before. Let's see what it is. Answer. There we go. 0, negative 1, negative 2, 1, 0, negative 1, 2, 1, 0. Great. Okay. Any questions or comments about this? So this is your first example of array broadcasting done in some detail. And it really is this idea of copying that is done automatically whenever you mix things and the shapes are lined up correctly. Yeah?
Would this work if the first vector is 3 comma?
Yeah, okay. This is a good point. So far I've told you the rule if the number of dimensions is the same. If number of dimensions is the same. So that is the rule if the number of dimensions is the same. There's rule number 2. Rule number 2. Rule number 2. What happens if number of dimensions is not the same? And this is where it really matters. Is it a 3 comma or is it a 3 comma 1 or is it a 1 comma 3? So, and the rule is, the answer to this rule is add ones to the left of the shorter one, the shorter guy. So if you have a 3 comma, it will turn the 3 comma into a 1 comma 3, and if that's what you wanted, it will work. So let's go back to this example. Let's make one that is called vec, and that will be shape 3 comma, np.array. We're going to do 1, 2, 3 here. It's because there's only one axis. It should be a 3 comma, and there it is, 3 comma. And when you do, if you do answer 2, if we make that column minus vec, what it will do, here's what I think it will do, unless now I'm nervous that I have it backwards, but I think this is correct. So if you do column minus vec, it's going to say, okay, column is a 3 comma 1, and vec is a 3 comma. And then what it's going to do is it's going to add ones to the left here until they are the same size, and then treat it exactly like before. So by rule number 2, it will add a 1 here. Let's do it like this. By rule 2, it becomes a 1 comma 3, and this thing stays as a 3 comma 1. And then by rule 1, the broadcasting rule, when they have the same shape, they will both become 3, 3 by being copied a bunch of times, and then they will be subtracted. So that's rule number 2. Let's see if it works the way I said. There's a chance I have it backwards, but I think I got it right. So, okay, it worked. Answer 2, and answer 2 is exactly the same matrix as before. It gives the same exact output as before. I will say it is dangerous. I get so nervous whenever I have code where they're different sizes, because I'm like, oh, what if it goes on the left or the right? And I get like really worried. So what I do is I always just put in the ones by hand. I'm like, okay, if I want to do 3, 1, and 3, before I feed it in, just like let me manually add ones until they're the same thing, and then I can be sure I know exactly where the ones are, right? Because there's no way in the code for you to see this step. It's hidden, right? Like I can't see, did it make it a 3 comma 1 and then add them together? Or like, I don't know. All I know is the output was 3 by 3, and then maybe it did something I wasn't expecting. So I always get really nervous, so I make it a 1, 3, and I try to avoid rule 2, but sometimes, it's useful. Fantastic question. Anybody else for questions here? Okay, so let's go back to the original problem. In the original problem, we had x was an n comma, and we wanted to compute this pairwise difference thing. So how did I do it? I made 2 versions of x. I made a column version of x, column x, which was n comma 1, and I made a row version of x, which was 1 comma n. And then I just did exactly what we did. If you subtract the row version of x from the column, if you take the column version and you subtract the row version, then you get exactly the n by n pairwise difference matrix. And that is what this code is doing. And so it is very sneaky if you're not used to it. When you see something like this, you're like, whoa, what is that? But this np.new axis, it says just add an axis that is size 1 and leave everything else alone. So really, you could write it in one line like this, but it would be nicer in your code to write x column, which is x, comma, np.newAxis. And this will say, okay, take x, the colon means pull everything out from that dimension, and just add a new dimension after that is size 1. So np.newAxis is make a new axis of size 1. So this will be an n comma 1, a column vector. Now let's run it, and let's see. So x is 10,000 comma, but x column is 10,000 comma 1 because we did this new axis to add a 1 to its shape. And similarly, you can do x row, which is x of np.newAxis, new axis, comma colon, and that will be 1 comma 10,000, right? So I added the 1, but this time in the front, wherever you put in the new axis, that will work. I will say one other thing you will see is instead of a colon means pull out the full dimension, whatever was in the dimension, pull that out. You will also see sometimes ... If somebody does ... that means all the dimensions. So colon means just the first dimension, and ... means give me all of the dimensions until the end. In this case, because x only has 1, it's the same thing. But if you see x ... comma np.newAxis, that means just on the end stick a 1, whereas x colon comma np.newAxis will only work if it's really a vector. So that's something you'll see. So watch out for that, those ... There is another thing you will sometimes see, which is, I think, to me it looks horrible, but I'm warning you guys if you see it in the wild. np.newAxis, you're like, okay, there's something with axes going on, we're making a new axis, it makes perfect sense to me. But this code will also work. You can put a none. None. If you put in none, it will just work. None and np.newAxis mean the same thing in the code. So if you run this, it will work. It looks great. Some people like it because none is less characters to type than np.newAxis. I personally think this is so confusing. What the hell is it? ... comma none. What does that do? I don't know. But if you know what it does, it's really saying take the thing, add a thing. So watch out for that. But now the solution is what we did before. You do x column minus x row, and that is the right answer. Let's call this answer. This is the same as answer. Let's do that. And answer now is this 10,000 by 10,000 thing, and it has xi minus xj. You can see it has zeros on that diagonal over here. Okay, so that's the first example of array broadcasting, and it really is super duper important for making programs that run somewhat efficiently in Python. Questions or comments about that? Okay, why am I telling you all this? Well, the rest of the class, for most of it, we're going to be going over that notebook with the canon problem, right? Trying to find the size of that window. And in that canon problem, we use array broadcasting a lot. So if you want to understand that code, you're going to see where is it that the new np.newAxis happens. And there's going to be some ... And I'm going to try to explain what it is so you really understand what it's doing. Because it's a very good example to start to learn how to do these kinds of tricks. And you really got to think in terms of vectors. Okay, should we move on to really doing that then? Let's start working on that. Is that the next thing? Yes, okay. So here is the code. And I'm going to set it to light mode. Light mode. And again, this is very similar to that Desmos thing I had, right? Where we slide the window, but we're doing it in Python. And in Python, you can really make that curve of the loss versus delta. And you can see where the minimum is, and that can help us understand what's going on. Okay, so the first little bit are NumPy NP, the plot, matplotlib.pyplot. This is how we plot everything. And there's this functools partial. Does anyone know what functools partial is? Okay, so functools lets you do things with functions. Partial is a way you can make a function more simple by feeding in a certain value. So if a function has 3 inputs, A, B, and C, you do partial, and you can make a new function where it inputs only A and B, and you've automatically set C to 1 or something. And we're going to use that to feed in the window size. So you'll see when we do it, it will feed in the window size. Okay, that's very, very standard stuff. Okay, it warns you, some crazy guy wrote this. Be careful when you run it. But hopefully it actually runs. Okay, great. Okay, so here is generating the data, and we're using the model y equals f of x plus epsilon. In real life, we don't know the function f, and we have to come up with a function f hat. Last time we did pen and paper math, and we came up with this decomposition. The mean squared error is the variance, the irreducible variance, the variance of epsilon, plus the square difference between the real f and the f hat we come up with squared. That is what we're doing. Okay, and here are some functions to generate toy data. X min and x max are 0 to 90, 0 to 90 degrees. And here is the secret function, which is the sine of twice the angle times 10. So if you shoot it at 45 degrees, then you will go 10 meters on average, and you will go less before. Let me get the Desmos open. So it's just re-implementing this cannonball, right? It's exactly this. The height was 10 here on the side. Okay. And there is a secret SD. SD stands for standard deviation function. And it's saying the standard deviation is always 4. And this ones-like command makes sure it's the right shape so that the vector that it returns is the same as the x. So x here could be a number, but it could also be a vector of entries or an array. And it's just going to apply this function to every single value of x and return something of the same size. So that is drawing this blue function and nothing else. Maybe kill everything else off here. And we'll just draw things as we go for what we have. Okay, so we don't have any data. We have this. That's what we have so far. We have this blue function, and we have that we're going to add a standard deviation of 4 everywhere. The variance of epsilon will always be 4. Okay. All right, and then here's the function to generate data. You give me an n, and I'm going to return a vector of size n. It would be nice if they wrote in the comments what the size was going to be, which I should have done, but I didn't do. So what we do is this vector is a vector of Gaussian distribution of size n, and then we do y equals secret mean function, f of x, plus epsilon. This whole thing is the epsilon. It's the standard deviation, that's the size of epsilon, times this noise, which is standard deviation 1, and we return x and y. And so what this does, when you run it, it will return a bunch of dots like this. The x and y values, x is in one array of size shape n comma, y is in another array of size n comma, and then you can plot them together. And that is over here, is the first plot. Let me actually run these as we go, and hopefully things will work. Okay, so that's what we have so far. Questions or comments so far? It's good, okay. And now we want to implement this thing. So we want to figure out f hat, which is this thing that we talked about, average everything inside some window, right? This was this thing from before. We had a test point, we had a window, and we're like, add up all the points that are in between, add them up, divide by the number of points, and that average will be that purple circle over here. That is the estimator. That will be our function, f hat. Okay? So that is what we're trying to estimate. F hat is the sum of the yi's, where we sum over all the places where xi is within delta of x. So delta is the window size. And then we divide by the number of points. And here is one way you could implement that in NumPy or in Python. This is I already showed you. Okay, this is what we're doing. So here is the implementation, or a possible implementation. You set n equals 0. You start y sum off at 0. You loop through all of the points, so I in range n. You look at all the n points. If the point is within x of xi, so in absolute value, if xi minus x is less than delta in absolute value, it's within delta of lowercase x. Then add the yi on, and add the 1 to the number of points. When you loop through this whole thing, that basically is computing the top. So y sum is the top, n is going to be the bottom, and then you return y sum divided by n. And this is a perfectly valid, this is like how you would think to do this thing, right? I gotta add stuff up, I gotta divide by some stuff. This is like where everybody's mind would go at first blush. But this, just like the other one, is a super slow way to do it. And if you do it the fast way, it is not 250 times faster, but 350 times faster. So this way is just too slow to do for all these points we want to do. If you do it this way, the simple thing we want to do would take like a long time to run. It would take minutes or hours to run. And you don't want to do that. So this is too slow. And we're going to figure out a way to do this with vectors where you never have to type in x of I, right? This is the whole point. You never want to type in x of I. You just want to deal with the whole vector x just at once and do it that way. And so that is I'm going to try to have you guys do. So I'm going to let you guys think about it for a bit. If you have a computer, you can really try it. And I will even give a hint for people who want the hint. So if you don't want the hint, I guess like cover your ears. I'll say the hint. And I'll give you guys like 2 or 3 minutes to think about it. The hint is, can you make an array of trues and falses, so a Boolean array that contains trues and falses, using x's and y's, so take the vector x, take the vector y, take everything you have, make a Boolean array of true falses to help you. And once you have that Boolean array, then you can do this quite quickly. And I made 3 options for you. One is I have no idea, which is totally fine. Number 2 is I can see how to make the Boolean array, but I don't know how to use that to help me. And number 3 is I think I have a solution. Of course, you don't have to be perfectly correct. If you think you have an idea, that's great. So I'll give you guys 2 or 3 minutes to think about that, because I think it will help you like intuit. Like if I just tell you the answer, you won't get a lot out of it. But if you think about it and then see this vector answer, I think it will help you learn this kind of stuff. So I'm going to give you, say, 2 minutes to work on that. Let's say 3 minutes. Okay. Yeah.
What is x?
Oh, x is all the x values from this, right? So in this picture, it's all the x values of the black dots, and y is all the y values. And so they're both vectors of size n. There's n points, n x values, and n y values. And x1 and y1 are the coordinates of the first point, x2, y2 are the coordinates of the second point, and so on.
How do I make those to try this?
Okay, yeah, let me give you, I can give you guys, this code is, here is the code that I have from before, so if you want to copy this down, exactly, you can do that. I did also put this on the GitHub, which it occurs to me I might not have given you guys the link yet. So let me do that quickly as well. But if you go to, there's a GitHub for the course, and there's 2 notebooks in it, and one of them is this one. So if you go mcnika89, that's me, and then you do data6100 underscore f23, that's you guys, and these are the notebooks for the course, one of which has this. It also has the solution, so if you scroll down too far, you will get spoiled. Okay, great question. Let me pause this for a sec. So yeah, so I have 2 vectors of size n, and there's some x value and there's some delta value, and this was the solution so far. That is the slow one, and then we're going to do the fast one underneath. Okay, let me see how many answers do I have so far. Who would like some more time to think about it? Okay, a couple people. Let me give you guys like 2 more minutes. I think it is actually helpful to think like, you know, I can show you the answer and then you go, okay, I guess it works, but it's really good to know, like, could you come up with the answer on your own, and how are you thinking about it? Yeah, let's keep this open for people who want to copy it down and try it. Yeah, and by the way, if you go to the GitHub, the top of every GitHub file should have a little link that says open in Colab, and if you open that in Colab and run it, then you'll have the whole thing and you can just run it on Google's computers. Otherwise, you can download it and run it on your own computer too. That's totally fine.
It doesn't GitHub link share somewhere?
Yeah, it should be on the website, but maybe it's not. It occurs to me that I might not have put it up because this is, I guess, the first class where we're using it. Let's take a look. Important links. Yeah, I guess it's not here. Okay, let's add it. Okay, there you go. Now it's posted as a link on the website as well. All right, 5 seconds left. Just put in your best guess. So if you have no idea, put in I have no idea. And then I will see how many people have ideas, and then we'll go based on that. So it's totally fine if you have no idea for this. Put in I have no idea. Anyway, when you get the mark for participating, and I know where everybody stands. Right, I think there's like 15 people here today. 3, 6, 9, 12, 15, 18. Okay, there's 18 people. 16, 17. Okay, that's close enough. Sorry, Mr. Last Person or Mrs. Last Person. Let's see. Maybe I miscounted. Okay, reveal. All right. So 11 people have no idea. 5 people can see the Boolean array, and only 1 person knows how they would do it. So let's talk about this Boolean array. And really, every time in your brain, every time you think of I need an if statement, you can almost always replace an if statement with making the array version of the same if statement. So this if statement is for every I outputs either true or false. Like this thing is either true or false. And instead of doing it for every single one, like is this one true, is this one true, is this one true, is this one true, just go and do it all at once and make an array of trues and falses. Does anybody want to, the 5 people who said how they can make the Boolean array? It's actually really easy to write in code. Does anyone want to say what you would do to make the array of trues and falses whose ith entry is this? You can actually do it. You can take what I highlighted and you can delete some characters. And if you delete the right characters, it will just make an array that is trues and falses. That's exactly what we want. Does anyone want to take a guess on what characters would you delete? This right now depends on I. How do we make it output a vector?
Okay, so can we delete the I bracket?
Yeah, let's see. What happens if we delete the I bracket? So this is, so here are my x's, right? X is some array of size 10,000. And if you do x minus x, so capital X is an array of size 10,000 comma, right? It should be appearing here. So x, here's x, 10,000 comma. If you do x minus x, let's call that step 1. Step 1 is also 10,000 comma. So it does array broadcasting. Lowercase x is a number, capital X is a vector, and it's saying, oh, I just subtract lowercase x from every single guy, right? And if you do np.absolute value of this, actually, that'll be step 2. Let's do it like this. And actually, why don't we print step 1? What's going to happen? Okay, yeah. So there's the first few numbers, right? So maybe I should print x first, so we can see what x is. Print capital X. Okay. So x was like negative 0.8, and then we did x minus x. It just subtracted 0.5 from every single number because lowercase x was 0.5. So if you do capital X minus X, where X is a scalar, then it will just do it to every single element of the vector. So kind of the default setup in NumPy is do something to every single element. Now let's add another step. Let's do step 2. Step 2, which is going to be the absolute value of capital of step 1, of X minus X. What is this going to do? Well, it's going to take the absolute value function and just apply it to every single one. Okay, so that's going to be step 2. Print step 2. Okay, so it took the absolute value. We went from negative 1.3 to positive 1.3, negative 0.9 to positive 1.9. 0.589 just left it alone, right? So it makes a vector which has the value of xi minus x, absolute value, in the ith position. And now you want to know, is it bigger or smaller than delta? So why don't we just do step 3 is going to be np.absolute value of x minus x, and just tell me, is that less than delta or not? And on its own, for every single I, this is either true or false. If you do it like this, it's going to say, is every single one less than delta? And tell me the answer. I do like to, whenever I do this, I always put brackets around it. Of course, that doesn't change the answer, but if you have an equal sign and then a less than sign later on, sometimes you can misread it. So I'm going to write it like that, and we're just going to output, what is step 3? And it's just, look, that's the array, right? Is 1.31 less than delta? False. Is 0.987 less than delta? False. Is 0.589 less than delta? False. I promise you some of them are true, but all the ones you can see, it happens to be false, and that is because delta is 0.1. Let's make delta a little bit bigger. Let's make delta 0.9, and to make sure it's working. And let's run this again. And now some of them should be true. So look, 1.3, is that less than 0.9? False. 0.987, less than 0.9? False. 0.589, less than 0.9? True. And the last couple are all true as well. Although, I don't know what happened with the 1.4. Anyway. Weird. I promise you it works. I don't know. Okay, let's pretend that it works. Now I'm very confused. Oh, I know what happened, guys. I know what happened. I reran this code block to make delta 0.9. But when you rerun this code block, it doesn't just run the last line. It runs all the lines. Okay?
So the random numbers
got regenerated. So okay, it's not these numbers anymore. Okay. So if you really want to do it, you gotta print this one again, and then tell me, are they less than 0.9? And now it makes perfect sense. 0.14 is true, 0.35 is true, 0.48 is true. Okay. So anyway, the point is, this code works perfectly well if you feed in a vector. You should take things where you're feeding in a scalar and think about what would happen if I fed in a vector, and almost always it's fine. It will just apply it to every single entry. Even if it's not a vector, if it's a matrix, it will do this to every single entry. It could have 10 dimensions. It'll just do that to every single dimension. So when you see an if statement like this, you should think, I'll just make the array version of this by deleting the I. Okay? And then it makes a big array where this is trues and falses. And once you have that big array of trues and falses, then you can try to compute these things y sum and n by looking at the whole array all at once, instead of looking at it entry by entry. So one example is n. N is the number of places where this is true. And again, you could write a for loop. You could say for I equals 1 to n. Is it true? If yes, plus 1. If not, do nothing. Then add them up. You don't want to do that. You want to do this in one line. So how would you calculate whether or not, or the number? So n equals, I want this to be the number of trues in the array. Anyone have an idea of what function we could use? So it's going to be something involving step 3. Step 3 was that Boolean array of trues and falses that we had before. Then you want to take a stab. What could we do to this array to count the number of trues and falses? What did you say?
np.countif.
Count if, yes. Okay, you definitely do this. np.count if, which is, I think, exactly made for this. I'm not sure of the syntax for this. Count, there is something like this. Let's Google it. NumPy count if. Counting, okay.
It might be mp.count and then maybe
Count.
mp.where.
Let's find it. Count, here it is. Count non-zero,
Oh,
right?
yeah.
Count non-zero. counts the number of non-zero entries, that will work perfectly good. So let's do this. Count non-zero. Non-zero. Was that what it was?
Yes.
A. So A here, you should get used to reading these documents because like this is how a lot of the coding works. A is the array to count non-zeros. If you specify an axis, it will only count it along a certain thing. If you do none, which is the default, then it counts all of the non-zero entries. Very good. And the number of non-zero things. Okay. And this will perfectly work because, let's see, capital N. Where's my capital N? So it's an int, and it's saying there's 5,723 things. Great. That's a perfectly good one to do it. There's another thing you can do, which is also useful, which is NumPy will count true as a 1 and false as a 0. So if you could think of this thing of falses and trues as equally well as zeros and ones. And if I want to know the number of ones somewhere, I could just add them up. So this is perfectly good with the count non-zero. But another one you'll commonly use is np.sum. And if you do that, let's call this n other way. Here's another way to do it. And it should come out to the same thing. N other way, it made it 5,723. It's the same number. Okay, it made it a different data type, which is interesting, but all good. So either way, you can either sum it or count the non-zeros. That is n. And look, we did it. We calculated the n's without doing any for loop. Okay. Questions or comments so far? Okay, let's do y. How would you calculate this y sum? Y sum is supposed to be the sum of all the y's where this thing has a true. Where this thing has a true.
We can use multiplication.
Yeah.
Yeah.
Very good. So yeah. So what do you want to multiply?
So three things. So whole sum will be y equal to y plus that thing.
Yeah.
And then we will multiply with it the Boolean value because
Great.
0 will yield 0 and
Yes.
1 will yield the value.
This is great. Okay, so let's give this Boolean thing that is exactly right. So let's give this thing a name. The Boolean array. Let's call that step 3. Right. So that's the Boolean array of trues and falses. And if you do y times the Boolean array, right, they both have the same length. Every single entry, it'll take all the ones that are 0 and just make it 0. Because the Boolean array gets treated as a 1 whenever it's true, you just do yi times 1, you just get the y values where it's 0. So y times Boolean array has zeros where it's supposed to be 0, and it has just the y value where you have the y value. So this is the y values of all the things we want to count. We want the sum of all these, so we just do np.sum of that. So very, very similar to before. Okay, and that will calculate it. And if you put it all together, you get this solution, which is right at the bottom. So the set of close points, you do the absolute value of x minus lowercase x is less than delta. I put it in brackets to make it easier to read. N is the sum, and y sum is the sum of y times that. And then you just, you got to do y sum divided by n. There you go. And it runs in 43 microseconds. So even though the other one is quite fast at 13 milliseconds, this one is like 300 times faster. Okay. So this is a good lesson in the kinds of thinking in terms of vectors. You'll notice when I did this, I never had to say xi, right? I thought of a way to come up with what I wanted, just thinking in terms of the vectors x. And there's never an x open bracket I. I never have to mention the length n. It just runs automatically. All right. Questions or comments about that one? Okay. The other nice thing about this solution is you notice that this Boolean close, it's doing what we wanted. But you can make this any function you want. And so like in the actual code here, let's unhide everything. You could actually put in any weight function you want. So instead of doing the sum of yi times 1 when it's close and 0 when it's not close, you could just say, just sum over any weight function. And if that weight function is 0 and 1, then it'll be exactly what we had before. So this WT is exactly what the function Boolean is close was doing in our code. So we can make that any function we want. There's no reason that has to be 1 and 0. 1 and 0 says count, when we're doing our original problem. Where did Desmos go? Ha. So when we're doing 1 and 0, I'm like, count everything that is in this purple, count that with a weight of 1, and everything outside, count that as a 0. But there's no reason to do that. I could say count things that are closer, count that like more than the ones outside. The one over here should contribute a little bit, but only a tiny, tiny amount. And so you can have a weighted sum. Instead of having 1s and 0s, you can say like, this one counts for a weight 7, that one counts for weight 3, this one counts for weight 0.1. There's no reason it has to be Boolean only. So if we go to this guy, you can do any weight function you want. So what weight function should you do? If you do 1s and 0s, that's exactly what we had. That does this. So if you just say 1 if it's within delta, 0 if it's not within delta, so either 0 or 1, you get exactly what we had before. But another common one that people do is a Gaussian one. And in general, you can do it for any weight function. So here is the code. Here's the code. So here's the weighted average estimate. And it inputs in 3 things. It inputs in the x values, the weight function, and the data for x and the data for y. And how does it work? Well, it applies the weight function to all the pairs of x values and data x. So for every possible x value you want to calculate and every data value, I calculate the weight function, those are the weights, and then I do the sum of the y times the weights, summed in the right way, and divided by the sum of the weights. That's kind of like y sum divided by n. And you'll notice the things I'm not saying are all the broadcasting details, right? Look, there's a dot, 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 comma, new axis, dot, 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 comma, new axis. That's what we started the class with. And there's also these axis minus 1. That means sum over the last axis. So don't sum all the points, just sum over the last axis. And what it is doing, it is broadcasting to make the data x size in the last axis. So whatever the size of x values you fed in, that's what you're going to get out of this function. If you feed it a vector, it'll calculate it for every single element of that vector. If you feed it just 1 point, it'll calculate it once. And so these broadcasting details are what make this function so fast, because when you go to draw this picture, if you want to draw the purple line, you don't just calculate one x value, you calculate every single point on the x-axis. And so by writing it this way, it's doing it with array broadcasting and with all the vector stuff we talked about. So that's the solution. There we go. So I'm not going super in depth on how the broadcasting works. If you want to figure it out, it's a good exercise for you to go and look at it. And this was the weight function we did before, right? Is x1 minus x2 less than window? If so, that counts as a 1. Otherwise, it counts as a 0. So this is the is close weight function, x1, x2, and depending on the window size, that was what we called delta. I also added on, the problem with this function is that if this thing is 0 always, if it's all zeros, then you're going to have a 0 divided by 0. So I added on a tiny, tiny number over here to avoid divide by 0 errors. So looking at the thing we wanted to do, f hat will sometimes be 0 divided by 0. So I added on some tiny numbers so that instead of being 0 divided by 0, it's like 10 to the minus 5 divided by 10 to the minus 5, like give me a reasonable output. And so I won't go into the details of why exactly I chose this, but it just makes sure, the exponential term makes sure that you don't have a 0 divided by 0. That way it'll work. Okay, so I have this function, the weighted average estimate, that's the f hat. I have the is close function, which you feed into the f hat. And I just looped over a bunch of different delta values. So I said, please make delta 30, 20, 10, 5, 2, 1. And then I have a for loop that goes over this. This for loop, okay, I said for loops are bad, but now I'm using a for loop. This one is fine. I just run it like 5 times. If you're going to run it like 5 times and it doesn't get worse as you get more data, then don't worry about it too much. You could also take everything and use array broadcasting to do all the delta values at once, but that's more work than it's worth. So just run over each delta, plot the x's and the y's, plot the secret value. Here I'm feeding in the x-axis. The x-axis is like 1,000 points, 1,000 x points, like 0.1, 0.2, and so on. And it does it all at once. So that's those are the blue line is made from the x-axis, and the dots are our data. And then I'm doing estimates, that's the f hat, which is the weighted average estimate where you feed in the x-axis for the x's. And the weight function I use, what is the weight function I use? The weight function I use is the is close function where I set the window size to delta. And this is where I use this partial func tool to make the function work for different values of delta, right? So the is close function normally inputs a window size, but here I fed in the window size of delta, and then it worked in the weighted average estimate. Okay, and then I feed in the data, the x's and the y's, and that gives me the estimates. And the estimates are exactly that green curve that is being plotted over here. So it has 1 point for every single point, every possible point on the x-axis. It does the calculation and figures out what it is and plots them all together. Okay. And there's some more stuff. I calculated the root mean squared error. That was by our formula. It's the difference between what you estimated and the true value squared. And then I plotted everything nicely. Okay. And I used the label command, so it makes a nice little legend on its own. And so we did that. We got it. Is all that work to make it do exactly what Desmos did, right? It's exactly the same thing. But you have to think about the implementation details when you do it in Python. Okay. Questions or comments about that? Okay. And then I did it. This was delta equals 30. This was delta equals 20. This was delta equals 10, right? Look, it's getting better and better. And you can see the root mean squared error, 4.5 here, 4.2 here, 4.1 here, and so on. And here it's getting worse, 4.28. And here it's even worse. This is 4.9 again. So this is like a horrible one. This is like horribly overfit. It's really chasing down the training points and going up and down and up and down. And so it's horribly overfit. So it's very similar to what we saw in Desmos last time. Oh, here's one that's even worse. Here's one that's even worse. 5.3 root mean squared error. Okay. Here is another example where instead of doing the like, are you close, it does this weighted thing. So it weights points by how far away they are squared. And it's missing a minus sign. Let's put the minus sign. Minus. Okay, minus. So you have 2 points, x and x prime. How much should the point x prime affect x? Well, it just depends on e to the minus their difference squared. So if they're very close together, this is close to 1. If they're very far apart, this is close to 0. And this is saying, instead of having this like cutoff of size delta, like everything in here counts the same and everything in here counts as 0, it's some kind of mixture of everybody. These guys count a lot, those guys count a little bit less, but there's some kind of smooth mixture going on. Okay, and if you do that weight function, all you got to do is define the weight function, and then the code is exactly the same, where you just feed in the weight function instead of the Gaussian weight function instead of the other one. And you get these nice smooth things that look like this. Because the Gaussian weight function is nice and smooth, instead of having jagged ups and downs, you get nice smooth things like this. And by changing this parameter sigma, it's just like changing delta. It's like what is closer or further away. And you get these nice smooth pictures that look like this. And when you get a small number, it's still going very jagged, but at least it's never like vertical, right? Like it's going up, down at a high slope, but it's not vertical. So it's a little bit nicer. Up, down, up, down, up, down. There we go. So this is when sigma equals 1. That's like saying the characteristic length scale is size 1, going up, down, up, down. All right. So that's the Gaussian weight, which we could have also done in Desmos. But here it is in Python. Questions or comments about this one? Yeah?
There is some items for sigma for delta.
Uh-huh.
For delta numbers, I want to know how can we choose because
Yeah.
randomly or
Yes, exactly. So the thing you should do is, the thing you really want to do is minimize the root mean squared error. And so what you should do is plot the root mean squared error versus this parameter delta or sigma. And that is what this does. So basically we ran this a bunch of times. For every single value, we can calculate the root mean squared error. Why don't we just plot all those on one axis? So this is just running through the whole big list and evaluating it. And you get a nice plot that looks like this. So on the x-axis is either sigma or delta. So delta for the nearest neighbor thing, and sigma for the Gaussian. And on the y-axis is the root mean squared error, how much error you have. And you can see that if sigma or delta is too big, like 30, you're averaging everything within 30 degrees, then you have a pretty high error. And if sigma or delta is really small, like 1 degree, you're averaging everything within 1 degree, then you also have a really high error. And in between, there is this nice sweet spot where the error goes down and then it goes back up. This is the optimal value to use because the error is minimized, which is what you want. So here, the true error is the root mean squared error is shown for the Gaussian, that's in red, and for the nearest neighbor, that's in green. And you can see the Gaussian one is a lot nicer. So just in general, the Gaussian one is smoother, more differentiable, kind of nicer to use. Whereas the nearest neighbor one has like weird jumps when like you cross some threshold on like how far the points are. So it's a little harder to interpret. So the Gaussian one is a bit nicer, but otherwise they're basically the same, very similar. I also did 2 dotted lines. There's a dotted line here at 4, So a root mean squared error of 4. Why is that called the minimum possible root mean squared error? Well, that's the irreducible error. So your best possible, even if you knew the function exactly, you would not be able to beat this because of the irreducible error. There's also a dotted line at yellow. The dotted line at yellow is like, what if you just ignore the x values and just try to estimate the y values without any x at all? Then you would get a root mean squared error of a little over 5. So like you can see, our model is close to the minimum possible, but not exactly the minimum possible because we only have a finite amount of data. And you can see we're doing quite a bit better than this constant estimate. So using the x values was helpful. Okay, so this basically so far, we spent an hour implementing it on Python, but we're basically exactly where we were last class, right? We had this model. We said, last class we did it in Desmos, and I said, oh, you slide this around, and you just see, is the error, is it going up or down, right? So here the error is going down, and you just try to minimize. And we said the optimal size was something like 10. So like 1 point, here 2.3, 1.7, 1.6, 1.5, 1.4, 1. Okay, so now it's going back up again, right? So I want to stop at around 1.39, I think is the minimum. So that's the minimum, right? And we just did it by sliding. Now we spent all this time implementing it in Python, and we can actually see what the minimum is. You can actually take the minimum and see where does it happen, and it's going to be right around 10 or 11 right there. So that's all stuff last class, basically. Now we're going to do a couple new things now, which we also talked a little bit about last class and what your videos were about. This is a great time to stop me for questions before I keep going. Okay, let's see. Yeah, go ahead.
Related to my previous question, I
Yeah.
want to know the number of the delta. Here is the list 0, 5, 10, 15, 20, 25. I want to know how can we choose the interval for this delta? Why we don't choose, for example, 1, 3, 6, 9, 11, 12 for delta?
These delta, these numbers 0, 5, 10, 15, 20, 25, 30.
Is the array in the Python, as you mentioned?
No, the array has hundreds of deltas. This is just the label. So I told Python do lots of different values, do 100 different values, and then plot it, but only label it with 5, 10, 15, 20, because otherwise there'd be too many labels.
You show the array for the delta.
Yeah, I can show the array. I think I did 100. I said go from 0 to 30 and give me 100 different ones.
What I mean.
Yeah. So here it is. My sigma array, you go between the min value and the max value and give me 100 values between the min and the max. So whatever the min and the max were, chop it up into 100 pieces and plug in that. And then I did the min and the max was 1 to 30, and so we split it up into 100 pieces. So the minimum is 1, the maximum is 30, split it up into 100 pieces. When we plot it, I only plotted 5, 10, 15, 20 because it looks nice, right? So this label has nothing to do with actually what it was doing. It's just the labels. And yeah, you could do more or less, right? Depending on how smooth your curve is, it's a very general problem. When you plot a function, how many dots do you need? I don't know. How long is a piece of string? Does that answer the question? Okay. Yeah, great question. Anybody else? Yeah.
How did you reach to the root mean square error of constant testing? Can you explain?
Yeah, the root mean squared error of the constant, it comes all the way back to, the root mean squared error of the constant. So you understand the irreducible one. Yeah, the constant one is it's the same problem that we started the course with the dice before we had any x values. The best thing you can do is estimate the mean of y. So if you didn't know the x values, you only had the y values. So imagine all these y values are marginalized. You have a bunch of dots on the y. And you want to estimate what it is, well, you pick the mean of the y, and then the variance you have is the variance of just the y values. So the variance of a constant estimator is just the variance of the y values where you ignore the x's completely. Yeah, and it's exactly for that reason we did before. Fantastic question, yeah. Anyone else? Okay, so what did we leave on last class? We said that in real life we said, this curve, okay, it's very nice. You have a minimum, you can calculate the error, it's all very good. But there's a fatal flaw in everything we did, which is that to calculate the root mean squared error, you need the difference between the f hat and the f, right? And if you knew the f, why are we doing this whole thing, right? The f is what we're trying to get to. Why the f are we doing it? Right? If f hat is what we're trying to get, and we're trying to make it close to f, then if you can measure the difference f hat minus f, then you don't need to do all this. So this is a nice theoretical curve, and that's why it's called the true error here. But in real life, you do not have access to the true error because you do not have access to the true function. So in real life, you only have the dots, and you do not have the blue curve, and so how could you measure this root mean squared error? And that is what the videos were about as well. And we saw this idea of having a training set and a test set that are separate, and then you hope that the error on the test set is approximating this error. So this is how to choose it in practice using a test set, and this is what your videos were about. Okay, so, and so what's going on here? Here, I'll just show you the pictures. The code is very similar to before. Now I've taken my data, and instead of just using it all directly, I have split it up into black dots, which are just like before, but also pink or magenta x's. And I call the magenta x's the test points, and I call the black ones the training points. And when I run my algorithm, I only use the black points to come up with f hat. And then the only purpose of the pink ones is no longer to find a better f hat, but it's to measure how good is my f hat doing. So I've really split the problem into two parts, right? Finding f hat and measuring how good f hat is doing. And I have two data sets, the training set and the test set, to do that. Okay. And here is, right, again, you can do a thing. This red function is only using the black points to be calculated. And it's doing that Gaussian estimate from before. And now you can estimate what is the root mean squared error for the test points. So you take the distance between every pink point and the red curve, and you square it up, and you add it up. And now you can really estimate what this is. So given only the dots with no blue function anywhere, you can do this root mean squared error test and say how far away are the pink points from that red curve. And then you can say, okay, if I change the Gaussian weight function, is it getting better or worse? So here they're 3.4 away on average. The root mean squared error is 3.4. And here they're only 3.0. So very good, 3.0. And here they're 3.3. So it got better for a while, now it's getting worse again. And here it's even worse, 3.8. And here it's really horrible. Here it's 4.3. And you can see, right, this red curve is trying to go through all the black dots. And by going through the black dots, there's lots of pink dots that you leave behind. Like this pink dot is like really poorly captured. This pink dot is really poorly captured. And so you can have a high error. So, okay. At least that's what it should be doing. Okay, here we go. Here's one where it's really crystal clear, right? The red curve is chasing down the black dots. And when you chase down the black dots, you leave the pink dots behind. And that's how you can see you have a bad error on the pink dots on the test data, right? And this is really the hallmark of overfitting, is if the red curve you captured using the black dots, if it's not informative about the pink dots, that means your model is overfitting. And you can see that again because the root mean squared error is quite high. Okay. Questions or comments about this idea? This was the idea in the videos as well, of having a test set and a training set, which I think is like the hallmark of data science and machine learning. This is like what separates very clearly like pure statistics from really data sciencey things. In pure statistics, you can have a way to measure the root mean squared error just by math or like some kind of trick or like figure out what's going on. But in data science, you say like, no, we're just going to do a train test split and measure everything that way. So this is like a really fundamental idea. I think this is like, in 10 years, maybe things will have moved on and like, there'll be a whole bunch of AI things that are different. It's a whole different field, but I think we'll still have training test error. This is like the most fundamental concept, is when you want to measure how well your model is doing, use a test set. Okay. Questions, comments? So just like before, you can plot the value of sigma. So I'm only doing the Gaussian model. You can plot sigma versus the root mean squared error. And using a test set, that's what I call the test set error, you get this nice red curve. So it's very high if sigma is too low, it's very high if sigma is too big, and there's a sweet spot in between where it's minimized. And because I also know the true value f, so the blue curve is the true error, which you cannot calculate in practice. So we calculated this red curve using a test set. The blue thing is what we would really like to know. That's what we would really like to do. And the point is that they have similar minimum values. So the minimum of the blue curve, that's the optimal thing. The minimum of the red curve is what we estimated. And they're somewhat close. It's not perfect, but that's one way you can sort of get at what is the optimal value of sigma just using a test set. Okay, and again, you'll see like all sorts of wonky things, right? Like the minimum possible root mean squared error is 4, but we think using our test set that it was less than 4. That's just random chance, right? The test set maybe is a little bit harder than the training set, or maybe it's a little easier. And maybe just by chance you do a lot better. Maybe by chance you do worse. So I would never say that this red curve is supposed to be the same exact height as the blue curve, but we have our fingers crossed and we hope that they have a minimum in a similar spot. And if they have a minimum in a similar spot, we can estimate what parameters we should use for our real life model. Okay. Any questions or comments about that one? Okay, so I do want to point out one common step that people often forget. So people do this whole thing, right? They take their data, they split it into a test set and a train set, and usually like it's common to do 20% of your data held out for a test set, and then they plot this curve, and they say the optimal value is sigma equals 18. And then they say, here's the model I calculated when sigma equals 18, right? Like, to calculate this, I had to calculate the model, the f hat for every possible sigma, and I report back the model with sigma equals 18. And there's one important step that people forget. So I'm going to ask you guys on Advertise. What is the important step?
Validation.
Well, validation is the whole idea. It's exactly what we just said. So this whole idea is called the test set, sometimes called the validation set, is use the test set to estimate the error. And we did that already. So here are the steps we've done so far. Divide the data into a training set and a test set. The test set is sometimes called validation. Run many models, i.e. try lots of delta values or sigma values on the training set. For each model, use the test set to estimate the error. Then use this error to estimate the best value for the parameter. So choose the best one, choose the one that gives you the minimum value, that's sigma equals 18. But there's one step at the end that people often forget. And I saw a lot of people forget it last year in this course on their project number 1. So I'm reminding you guys right now, there's one step. Once you have the best possible sigma, there's one more step you got to do. And I will give you just 1 minute. Put in what your guess is, if you remember. If you don't remember, put in I don't know. But what could the last step be? And remember, at the end of the day, we want to come out with the best possible model, right? Given our data, we want the best possible model that we could use. Okay, put in your guesses. What is the important last step that everybody forgets? So we had our train test, we split into training test, we ran the model a bunch of times, we figured out the minimum error on the test set. So we figured out, okay, I think sigma equals, what was it, 18 is the best. And then now what do we do? Let's see what people said. I don't know, validation. One person has exactly the right answer. Retrain with the best delta. So once you know the right answer, you know that sigma equals 18, you can improve your model by using sigma equals 18 on the entire data set, right? So this red curve is only trained on the training set, and the training set is only 80% of the entire data set. So if at the end of the day you want to come back with the best possible model you can do, you should rerun with sigma equals 18 on the entire data set. And you will not know how well it is, like how well it does, right? You will not be able to compute an estimate for the error because you're using the entire data set. You have no test points left over. But presumably, that model is better than this model that has sigma equals 18 and only on the train set, right? So don't forget to redo the model on the entire data set. So congratulations to whoever remembered that. That was one of the messages in the video that I think is easy to forget from those pre-class videos. Okay, any questions or comments about that? I have one last little thing here coming up, but it's kind of more of the same kind of stuff. Okay, so let me show you the last little bit is this idea of the leave one out error. So one thing, and this is the same idea with why you should rerun it, is when you do this train test set split, you are making your training set worse because you're reducing the amount of data you have, right? You had 100% of your data, and then you went down to 80% so you could save 20% for some other thing, and that makes your model worse if you only have 80% of the data points. So one way to try to get more data points in is to do this leave one out error. And leave one out, or also called the LOO, L-O-O, is what you do is you go through your data points and you, one by one, you run the model a bunch of times with only one pink X per time. So you say, today is your turn to be the pink X. And then you run the model. And then you make it back and go black dot. And then you say, now it's your turn to be the pink X. And you make that one the pink X. So instead of running it once with 20% of pink X's, you run it many, many times with exactly one pink X each time. And then you do the average of those errors. So that is what this code does. And it's not super complicated. It just runs through everything. It does the estimates a bunch of times. So it does it for each sigma. Yeah, and if you read the code, you'll see I did it with array broadcasting. So instead of doing it once and then another time and then another time, I said, put them all in an array, do it one time, and do all of them. So if you want to read the code, you can see some cool array broadcasting. I'm on the wrong thing. Okay, I'm here. Okay, no, I didn't do it with array broadcasting. Look, I have a loop. So I broke my rule about don't do loops like that because I was lazy. I should have done it with the array broadcasting. So look, I deleted one point from the training set, and then I put that one point in the test set, and then I just ran the model. So you take the whole test set, you take the whole thing, you delete one point, you put that point in the test set, then you run it, and then you average over all the errors you get. And that's called the leave one out error. The leave one out error. And if you do the same kind of thing we did before, plotting the real value versus your estimate using a test set, here is what it looks like with the leave one out error. Here's what it looks like. So the true error is in blue, and the leave one out error is in red. And you can see that they're a lot more similar now. And that's because the leave one out error, you're only leaving out one point at a time. The real model you get is a lot closer to the real thing. And by doing this leave one out thing, you have a more accurate estimate for the leave one out error. Okay, I'll leave you guys with this one final question then. Why doesn't everybody do this leave one out thing? This leave one out thing is so much better. But there is one serious disadvantage, which is why you need to know both. You need to know the classical way, and the leave one out way is also good to know. Why would you do, what is the major disadvantage? And I'll give you just 1 minute to do this. Tell me the major disadvantage. If you've been paying attention, I think you can figure it out, or maybe you remember it from the videos. Okay, 25 seconds left, so put in your guesses. What is the disadvantage of the leave one out? Okay, 3 seconds left. Okay, what is the disadvantage of the leave one out error is too many iterations, very good. Expensive computation time, computationally intensive. These are all the right answer. Time consuming. More variance, I think, it has less variance. So if you do something many times and you average, the variance goes down. But it is time consuming because you have to run the model many, many times, right? In the real train test split, you train the model once on the training set, you measure on the test set, you call it a day. In the leave one out, you leave one point out, and then you have to train the model every single time you leave a different point out. So it takes a long time, and that is why people don't do it in practice, because usually people have a model that takes some non-zero amount of time to train. Sometimes for very big machine learning models, it can take months and months to train, so you don't have time to rerun it on your data set. And that is why people just do it one time, or sometimes they'll do something in between a leave one out and a regular thing. They'll do it 5 times or something. That was the idea of cross-validation, splitting your data set into 5 from the video. So depending on your balance of how quickly your model can run and how accurate you want the error estimate to be, you can do something in between leave one out and the regular train test split. And it is up to you what you want to do. So if you can write really fast code, then the leave one out error is great. You should definitely do the leave one out. And in this case, it runs in like 1 second, right? So, and the reason it ran so fast is because I did a lot of array broadcasting. I made sure all the steps, the weighted average estimate was the fast way to do it. That's why this was okay. Okay, it is 11:20. That was the last thing I wanted to say. I did also post, for people's interest, some rough details about Project 1. So Project 1, here's the broad outline that has been posted online now. And there's going to be more details posted soon, but you can play with it already if you want. So the project is going to have 2 parts with 1 data set. In the data set, it's the Ames housing data set, and I gave you 1,000 pieces of information about house sales in this city of Ames, Iowa. So in the thing, every row is a house sale, and it tells you how many bedrooms the house had, how big is it, things like that. And your job is to predict the sale price. So using the data set of sale prices and information about houses, you need to come up with the best model you can to predict the sale price. If you want to, you can use the kind of averaging thing that we have been doing so far. On Thursday's class, we're starting linear regression. You can also do this problem with linear regression. That would also be perfectly valid. And you're going to have to submit a function that is predicting sale prices. And I also want you to make a plot, just like we did in today's class, that shows the overfitting to underfitting U-shaped curve. So you're going to use this data set to make something that shows this kind of shape. I want to see this kind of shape on the x-axis. You can put whatever you want, but I want you to try a bunch of different models, calculate the root mean squared error, and show this kind of U-shaped curve. And then you're going to do the minimum, and you're going to submit that. That will be your submission for part 1. So more details coming soon, but the data set is posted if you want to start to play with it. We're going to start linear regression on Thursday, and that will probably be the basis for a lot of people's project as well. It's going to be due in right around 3 weeks from today. So it's the Friday right before Thanksgiving. Okay, I'm going to stop there. If you have questions, please come up. I'll be here for a few minutes. All right, see you guys next class.